Okay, so welcome everyone. Thank you for joining us again. And today it's our pleasure to hear Alok Laddha, who will tell us about infrared triangles and asymptotic symmetries and soft radiation. Please.
I can start now, right, Mark?
Yeah, please.
Yeah, okay. So let me start by first thanking Mark for inviting me here to, this is my first actually even attending the non-local quantum gravity seminar. So this is the title of my talk, Infrared Triangles, Asymptotic Symmetries and Soft Radiation. And at least what I hope to do in next 1 hour is to give kind of an overview of where we are in understanding these three different ideas which have come together in last few years. So, So let me start with some motivation. So as I guess most of you would know that quantum gravity as matrix in asymptotically flat case is constrained by a hierarchy of relations in the infrared. And in fact, these constraints manifest themselves in many forms. For example, as infinite dimensional symmetry of the S matrix that we will look in some detail in the talk, and also as a universality of classical low energy gravitational radiation, or what is called the classical soft radiation. And it turns out that we can synthesize these different aspects of these infrared constraints into an abstract structure, which is called the infrared triangle, which was first proposed by Pastersky and Strominger in 2015. And here is the basic idea behind the infrared triangle. It has three vertices, where it's just an abstract triangle which tries to capture three distinct ideas. So on the top vertex we have what are usually called asymptotic symmetries. They're usually infinitely many. And on the left side of the bottom vertex, we have something called classical soft theorems. And these classical soft theorems basically are certain class of observable effects in classical general relativity, which are really related to the low energy physics of the theory. And then there is on the other vertex, we have what are called quantum soft theorems. And it turns out that the idea behind the infrared triangle is that these three, very different looking objects, some symmetries or conservation laws, some quantum soft theorems, which are constraints on the amplitudes, and some classical observables like the memory effect. They are really basically just the same, just manifesting themselves in different guises. So this is a general idea of the infrared triangle, and the reason this sort of people thought of this Pastersky and Strominger is because there was an example already in the literature which has been known for last 8 years, and this is the first example that is known is which it relates three things. One is what is called the Weinberg soft graviton theorem, which is a constraint on the scattering amplitude on the quantum amplitude side. On the classical observable side, it captures the classical, very well-known memory effect. And on the conservation laws or asymptotic symmetry side, it captures the super translation symmetries as symmetries of the S matrix. And it turns out that, as you will see in the talk, that these three are really same things. They just manifest themselves in different ways. So here is this infrared triangle, which is sort of the one that is most understood by now. So by ST, I just mean the super translation charge, which is associated to what are called super translation symmetries of asymptotically flat spacetimes. And ST hat is what we get by quantizing this charge. And it turns out that the conservation law for the super translation charge is simply the statement of the memory effect. And if we quantize it, then the word identity we get from the super translation, from the quantized super translation charge, is simply the statement of Weinberg soft theorem. And it turns out that there is a very precise way in which we can take a classical limit of the Weinberg soft theorem and obtain the classical memory effect. So the entire triangle kind of closes. And the reason this triangle is interesting is because it's powered by universality, in the sense that we have three different results which are exact and universal in the sense that the memory effect, as is well known, is an exact result in full nonlinear general relativity. Weinberg soft theorem is an exact constraint on the perturbative scattering amplitude of gravity, which is valid up to any loop order. In fact, it's even true for perturbative string amplitudes. And super translations, classically, of course, it has been known that they are symmetries of the full nonlinear general relativity, and now it has also been understood that they are also symmetries of perturbative quantum gravity scattering amplitude. So these are, they are kind of interesting results which are in some sense, as you will see more, they're independent of the details of the theory and their exact results. So what we want to do in this talk is to try to classify various infrared triangles that constrain the quantum gravity S matrix in D equal to 4 dimensions, but also in in D larger than 4 dimensions. So and there's a related question that since these are really constraints on the infrared sector of the theory, how do we parameterize the space of all the vacua of quantum gravity? I mean, this analysis of infrared triangle, does it shed any light on what are all possible vacuum states of quantum gravity? So also I should say that please, I don't really have any goal to reach, so stop me anytime and ask questions. So this is the plan of the talk. Mark, you can hear me okay, right?
Yes, perfect. Thank you.
Okay. So here's the rough plan of the talk. I will start with some very brief introduction to quantum soft theorems, then introduce the ideas of asymptotic symmetries, which are which include super translations, but now there are other new asymptotic symmetries which people have discovered, and then we will see how the soft theorems are related to classical and quantum conservation laws, and then finally we will see that what are the new how many such infrared triangles we have, in the sense that how many such infrared constraints we have on the quantum gravity S matrix. Okay, so I'll just start with a review of the soft graviton theorems. I mean, of course, one thing that when we talk about soft theorems is that we wonder how this could possibly make sense, because S matrix is of quantum gravity in 4 dimensions is known to be infrared divergent. But the nice thing about soft theorems are that they don't really refer to the S matrix, but they refer to ratios of 2 S matrices. In other words, you just look at, so the script M is the scattering amplitude, which involves n momenta. They could be momenta of any particles with any spin, and 1 graviton, which we take to be soft. That is, we take its energy to 0. So it's a ratio of the amplitude involving 1 soft graviton and the amplitude which does not involve the soft graviton. It turns out that this ratio is infrared finite, and so it makes sense, and it has a nice expansion in the frequency of the graviton. And these are the first 2 terms in the expansion. So the first term is a simple pole in omega, and as we will see more, it's called the Weinberg soft factor, and this has been known from 64. And the second term, which was only proved recently by Bishwajit Sahu and Ashok Sen in 2018, which is called the logarithmic soft factor, which depends on log of the frequency. And then there may be subleading terms, but they, as we will see, they are not universal. They depend on the details of the theory. Okay, so just to give you a little more, but this is an exact result in quantum gravity. But you can ask, okay, what about if you start with something simpler, like say tree-level scattering amplitude, then we get something which is nicer.
I think Laurent has a question, maybe.
Yeah,
yes.
Can you go back? Because you're going fast on this log of omega. So maybe.
Yeah.
Are you going to explain more where it's coming from?
Yes, I will explain more, Laura. I just wanted to just introduce the statement. Yeah, I will certainly say a lot more about this. Is that okay? Or
yeah, it's okay.
Okay. So okay, but we can ask, okay, what about if we do something simpler, like look at tree-level scattering amplitude? Then it turns out that the soft expansion is it's nicer in some sense, in the sense that there are none of these logarithmic terms. So there is the Weinberg soft factor, which remains unaffected, which is the first term. I'm sorry, there should be a plus between the S0 and the S1. And the S1 is what is called the subleading soft factor. As the arguments of these factors indicate, the S0, the Weinberg soft factor, only depends on the momenta of the scattering particles and the direction of the graviton. K is the momentum of the graviton, so K by omega is basically just the direction. And this S1, which is the subleading soft factor, depends on the angular momenta of the scattering particles and the direction of the gravitons. So that's the statement of the theorem for tree level scattering. And then there are if you go further in the frequency expansion, then there are order omega terms, but they are not, they start depending on the theory, so they are not as interesting as these 2 terms, which are really universal. So I just here give a little bit more detail of these different soft factors. So I mean, the expressions are not very important for us, but just to give you a flavor. So the Weinberg soft factor really, it just depends on the momenta of the scattering particles, and it has this nice little form. And the subleading soft factor for the tree level scattering is, as you can see, it's linear in the angular momenta of the scattering particles. And this is related to the partly related to the question Laura was asking, that if you, when we look at the exact soft theorem statement, there are these logarithmic soft factors which depend on the momenta, but they depend on momenta in a very complicated way, in the sense that they are sum over pairs of the scattering particles. So the expressions for this S log are very, very long. But what is interesting about all these three factors, especially S0 and S log, is that they are completely universal. So in the sense that, you go to 2 loops, 3 loops for the scattering amplitude, the S0 and S log does not change. And S1 is universal in the sense that if you look at tree-level scattering for gravity, or you add any higher derivative interactions to Einstein's theory, the S1 does not change. Even though the tree-level scattering amplitude itself changes, if you do a soft expansion, the S1 will not change. So all the three soft theorems, they have this interesting universal character. So this is what I say here, that S0 and S log are really truly universal in the sense that they are independent of the higher derivative interactions and independent of the loop order that you look at. So in that sense, they're completely independent of the details of the scattering, and they are one loop exact in the sense that S0 in fact is tree level exact. It has no correction beyond tree level. S log is one loop exact, and it has no correction. If you look at the infrared effects coming from higher than one. And now here is one interesting about this S1 that we looked at, which was the subleading soft factor for tree level scattering. That it's actually if you're in D greater than 4 dimension, then as was shown by Ashok Sen in 2017, that there is no log omega term. There is only the expansion is really the this power series expansion, and S1 is the universal soft factor, the one that we exactly wrote down here. So in D greater than 4 dimension, the statement of the soft theorem is precisely the one that is written here, and in D equal to 4 dimensions, it is this one. So that's so if there is any question about soft theorems, then we can discuss it now.
Yeah,
yes.
I have it's about this log theorem. So maybe two questions. One is how come people kind of missed it before, and the second question is, because you say it exists only in 4 dimension, yes, is it related to the fact that in gravity? You're talking about gravity or gauge theories there?
Yeah, gravity here. So we will come to the physics of this log in the talk, of course.
Okay. Because in gravity, is it so? Are you going to relate it to the fact that in 4 dimension there's also a potential logarithmic asymptotic?
Exactly, it's related to that. Exactly. Yeah. So regarding your first question, why people missed it before, I'm not entirely sure. I mean, I think people did not really look for people probably did not look for the subleading soft theorems, in the sense that even this S1 that is written in the second line here, that was found only as in 2012 for gravity by Cachazo and Strominger. So I think the fact that there could even exist these soft theorems beyond leading order, I think people probably did not anticipate. I guess that would be one reason. Yeah. I mean, the reason that people started looking at the soft theorems came from asymptotic symmetry. So I'm not sure, maybe there was not direct motivation to look for the soft theorems, before.
Okay.
But yeah, so we will look at the details of the physics of the S log in the talk, as you are saying. They are related exactly to the Coulombic potential, 1/r effect in 4 dimensions. Okay. So now, so this is just some nomenclature that S0 is usually called the leading soft factor, S1 is the subleading soft factor, and S log is the log soft factor. So if I just use it loosely, then you just know which one I'm talking about. And okay, you can ask, is this all? And it turns out that actually, at least in higher dimension, there are more interesting soft theorems. So at what we would call a subleading order, which is order omega, this n+1 amplitude again factorizes into a factor which is which again depends on the angular momentum of the scattering particles, and this S2 is most cleanly understood in D greater than 4 dimension. And it turns out that the S2 is, but it turns out this S2 is not really universal, in the sense that it depends on the 3-point couplings in the theory. So if you add to, say, Einstein-Hilbert action, a term which is, say, a scalar times Riemann square, then even though the factorization itself holds, in the sense that your amplitude will be S2 times the n-point amplitude, the form of the S2 is depends on the 3-point coupling. And then it can be seen that there really exists no factorization as such beyond order omega in this power series expansion. But as we will see later in the talk, that there are certain conjectured universals of theorems remarkably in 4 dimensions, which are at different orders in log omega, like at order omega to the m, log omega to the m plus 1. And this, there has been a lot of progress on this, at least in the classical theory by Vishwajit Sahu in last year, which we will discuss in towards the end of the talk. So this is kind of the status of the sort of the hierarchy of soft theorems in quantum gravity in 4 and higher dimensions. Now, okay, so that was one of the vertices of the infrared triangle. So now I'm just going to quickly review the second vertex, which is the asymptotic symmetries. Of course, here most of the audience knows much more than me, so I will be brief. Just again, this is something very, very basic. Just to recall that because we are interested really in scattering, the most relevant boundaries for us are the Scri plus, Scri minus, the null infinities, past and future null infinities, and past and future time-like infinities. And as I'm sure everyone knows here, these past and future null infinities are cylinders with coordinates usually being parameterized by u and v, and there are different compactification for the time-like infinity, but the one that is useful for scattering is if you blow up time-like infinity into a Euclidean ADS, which turns out to be useful to study for studies of asymptotic symmetry. And so first, but anyway, first let's look at the physics at null infinity, or more specifically at Scri plus. And it turns out that the space of all we can parameterize all asymptotically flat geometries in this way. This is kind of like the Pfeffer-Van Graham expansion in 1 by R close to null infinity. And so the green tensors are the ones which are most interesting for us. So QED, of course, is the unit, is a sphere metric on the sphere at infinity. MB, which is the 1 by R correction to the du square, is what is known as the Bondi mass aspect. And perhaps the most important object in the game is the shear, which is sort of the free data which determines everything using equations of motion, which is the CAB. And it turns out that actually there is a space, there is a freedom that you can actually deform the shear by a linear in U term, which I have just denoted as TAB. So these x's are the coordinates on the sphere. So TAB is just a function on the sphere. It doesn't depend on U itself. And this TAB it turns out that TAB is non-zero if and only if QAB is not a unit sphere metric. So if you work like in the olden days, like BMS did, where your Q was just a unit sphere metric, then T will be 0 and you will only have the CAB as the term in the shear. And NA is what is usually called the angular momentum aspect. So NA and MB are determined in terms of the shear data. And so really in that sense, the free data is the sphere metric Q and the shear field CAB. And there are, of course, there can be subleading terms, but I just focus on the ones which will be relevant for the talk. And the structure of this tensor TAB was analyzed in 2 very nice papers by Geoffrey Comper and his collaborators, and Miguel and Peraza. So I just think that TAB is not a stress tensor or anything. It's just a tensor which depends on the sphere metric, and N is what is usually called the angular momentum aspect. And of course, as probably everyone knows, that the radiation information itself is contained in what is called the News tensor, which for arbitrary sphere metric Q is just the U derivative of the shear plus this tensor T. One explicit way to see that the radiation data is contained in the News is to just look at the energy flux at Scri, which which is just a UU component of the stress tensor, which depends on the News explicitly, and whatever the massless matter you may have in your theory, which may be leaking out to null infinity. Okay, so that's the structure of the space of all asymptotically flat geometries, and now we can ask, what are the all possible symmetries in the sense that large diffeomorphisms which preserve asymptotic flatness, so which map a asymptotically flat spacetime to another asymptotically flat spacetime. And this result, there is the old version of the result is what is known as the BMS group, where it was noticed that the asymptotic symmetries are not simply Poincare symmetries, but they are enhanced by a infinite dimensional super translation group, which is just parameterized by some functions f on the sphere. So these vector fields xi f are what generate super translation at future null infinity. And in the old BMS group, you had the super translations, and you had the you had the Lorentz group, and that Lorentz group was parameterized in terms of just a global conformal killing fields on the sphere at infinity. So that was the full space of asymptotic symmetries. but recently it turns out that there have been two extensions to BMS. One where because you have because the Lorentz group is parameterized by SL2C vector fields, you can enhance them in two different ways. One is to use the usual Virasoro extension and just use holomorphic or anti-holomorphic vector fields, which are an infinite dimensional extension of SL2C, or you can just embed SL2C into smooth vector fields on the sphere, so which is usually the group of smooth diffeomorphisms. And as we will see, both of these groups are kind of important for the soft for the infrared triangle. So these groups where you there are two possible extensions of BMS algebra. One where you enhance Lorentz group to or Lorentz algebra to Virasoro algebra, and the key difference is that when you have these Virasoro symmetries, if your vector field V is local conformal killing field instead of just being SL2C, they deform this tensor T. So if you had the Virasoro, then they deform the tensor T in the way that is written there. And away from the points where the vector field has a pole, they do not change the sphere metric. But if you enhance the Lorentz group to smooth diffeomorphisms, then they because they smoothly deform the sphere metric, and the way they deform is written in the equation, the last equation in this line, which is delta V QED equal to the Lie derivative minus some conformal transformation. So this is just to show that how what these symmetries do in addition to the BMS. So they have the effect on the metric on the sphere or on the tensor T on the sphere.
Yes, sorry, it's going very fast. This TAB, can you say more about it? Do you have an expression in terms of the metric?
It's intrinsically determined in terms of Q. I think there is no local expression. I don't remember the exact expression, but it is determined solely in terms of the metric Q. So so if you just start with the unit sphere metric and do a meromorphic transformation, then it turns out that your sphere metric is not changed away from the singular points, and then the T is just the Schwarzian, of that vector field. So maybe that's one.
Is it the same as the Geroc tensor?
Yeah, I think it is. I don't know if Miguel is in the audience. It is probably same as the Geroc tensor. Yes.
Okay, and I'm just confused by the way you look at the transformation metric. If I make a diffeomorphism on Virasoro changes the metric by a conformal factor. Here you're saying that delta V of Q is equal to 0. So
yeah, it's 0 away from the, I just wrote it 0 in the sense that just to highlight the difference from the smooth diffeomorphism. So it is 0 away from the points where the vector field has poles, because it's a conformal transformation. Because you see delta V, if you see delta V for the diffeomorphisms, it has the Lie derivative term minus the conformal scaling term. So if you are, naively, if your LV of QAB, if your V was a conformal killing field, then LV of QAB also will be the, the divergence of V times QAB. So it will cancel, if you just, the two terms will cancel each other. So it's not that the Lie derivative of the metric is 0, but the
it's the combination. Very good.
Yeah, it's a combination, right? Yeah. So thanks. Yeah. Sorry. Yeah, I just went too fast here. So if there's any other question.
So okay. Yeah.
Yes.
Yeah. I don't know. Maybe it's too much of a technical question. We can chat about it. The fact that you include the DV means that this guy is not a Lie algebra anymore. It's a Lie algebroid. So it's a bit of a.
Okay. So I see what you're saying that what is the you're saying what is the algebra of this vector of the vector fields, right? That's the So we will actually, this is one of the points that we will discuss.
Okay, so you agree it's not an algebra, it's an algebroid, and that's problematic at the quantum level.
Exactly. Yeah, I will come to that. I will come to that. That's one of the issues that we will touch upon. Yeah, for sure. Yeah. That's the one of the main I think problems that we are trying to understand better. So these are the symmetries. So now we can ask, okay, can we compute charges for these asymptotic symmetries? So basically using phase space techniques, and of course, because these are asymptotic symmetries, it's probably best to look at the phase space which is defined at at null infinity, because these are the vector fields which are defined at null infinity. So maybe first what we can do is start something simple and try to look at the BMS charges for the old BMS group, not without worrying about these extensions. And so let's fix this sphere metric Q to be the unit sphere metric like Bondi and others did. And then, as was shown by Abai and Strubel in 81, that there is a nice, the covariant phase space of general relativity can be parameterized in terms of this shear. And so, and the fall off condition of the shear field as a function of U is given there. So, if for generic initial data of GR, shear satisfies these fall off conditions, and as they showed that with these fall off conditions, you have a nice Poisson bracket structure at null infinity, and these are the elementary Poisson brackets that they derived. That the two news, are roughly speaking conjugate to each other in the sense written here. So once we have these Poisson brackets, we could write down the charges for the asymptotic symmetries. But we have because we are interested in the scattering problem. So we have two boundaries. One is chi plus and one is chi minus. And in principle, we have two different BMS groups. One is chi plus and one is chi minus. And in general, they don't talk to each other because they are defined independently as chi plus and chi minus. But that would not be very useful for us if you want to study scattering. And it was shown in a series of, initially it was shown in sort of perturbative context by Strominger and others, that for the scattering we have to look at the sort of the diagonal subgroup of the BMS group, where the generators of the super translation at chi plus and chi minus are related as defined in the last equation. So F plus is the BMS super translation function at chi plus, and it has to be identified with the super translation function at chi minus by an antipodal identification. So xa being the point on the sphere, and same with the SL2C vector fields, which have denoted as YA here. And so intuitively the reason that antipodal identification was thought of was because if you just draw a light ray from a point on a sphere at chi minus, then it will hit an antipodal point at chi plus. But okay, this is a very flat space intuition, and so we have to really prove that with this kind of identification, the BMS charges are indeed conserved between chi plus and chi minus. And there has been some very nice work in this by Karthik Prabhu and his collaborators in recent past, where they have actually shown in nonlinear general theory that super translation charges are conserved with this identification, antipodal identification. But but we can first start with on this Asteker-Strubel phase space. We can actually explicitly, because we have the Poisson brackets, we can compute the super translation charge, and it is a very nice expression. And we can see that all the fields we introduced before kind of come into play. So we can write it in two different ways. One is an integral over the null infinity, where it is it is just roughly speaking, it's the flux of the stress tensor. If you have matter, TUU is the full stress tensor which is sitting at chi. So this is a term which is usually called the hard charge because it's quadratic in the fields. And then there is an additional term which is a little bit surprising, which is linear in the news tensor, which we will come to in a moment, and which is usually called the soft charge simply because it's linear in the irradiative data. But the same charge can be written as simply as a sphere integral at U equal to minus infinity, which is kind of similar to how we will write the total charge or total mass in the ADM formulation. The only difference is that we have to smear the mass aspect with the function f, and so we have infinitely many charges now because this f can be any function on the sphere. So we have derived infinitely many charges, and the statement is that these charges are conserved. Infinitely many of all these charges are conserved if we do the antipodal identification between f plus and f minus. So this is a class of charges we get with the old BMS, and we know if we had, of course, then we will have the angular momentum charges for the Lorentz group, but these are the new ones we will get in addition to the energy linear momentum and angular momentum. Okay, but we can ask now what about super rotation charges, where these vector fields can be either Virasoro or smooth diffeomorphisms, and here I'm just focusing on pure gravity just for simplicity. So again the expression is structurally a little bit similar to what we saw earlier. So there is a term which is quadratic in the shear field or in the news tensor, which I have written in which is the first term, and there is a term which is linear in the news, except there's a subtle difference that it's not integral over news, but integral over u times the news. And this really, as you will see, it makes all the difference. And this, I will come to O and F in a moment. I mean, the expressions are not very important, but the exactly as in the case of super translation, we can write this super rotation charges as, angular momentum aspects at spatial, roughly speaking, spatial infinity or at u equal to minus infinity, again smeared by this vector field V. So, they have a nice form in terms of the angular momentum aspect. And this O and F are just some functions of the vector field V, and O is really a differential operator which acts on C as written here. So it has a Lie derivative, it has a conformal scaling, and it has a U derivative. And F is just this factor that is written there. So yeah, so that's they depend on the vector field and the sphere metric, but that's about it. So those are the charges. So now we have kind of understood two vertices of the infrared triangle. One is the quantum soft theorem, and one are these charges for the super translation and super rotation. And now we have to find the third missing vertex, which we call memory effect or classical soft theorem. So maybe I stop here and see if there are any questions.
Well, I had a question back then.
Yes.
You mentioned the definition of the Ashtecar-Strobel phase space, but this definition is not, it's not it's not the right one. Like this condition, it's not the right one if you want to extend your symmetry as you want. Like if you extend.
Yes, we will come to the extension. Yeah, we will come to the extension. So this one really, this one really worked with the old BMS, and even though we could have, even though we could have derived the super rotation charges, they do not preserve this phase space. So as we will see that we have to extend this phase space. I will just come to that in a moment. That you are completely correct. That the phase space on which all the asymptotic symmetries are well defined is an extension of this phase space. Was that your question, Laurent? Or?
Yeah, no, that was exactly my
Yeah. We will come to that. Yeah.
Sorry, you went a bit fast. Can you show us again the super rotation chart? You went a bit fast, like on this operator.
Yes.
Maybe you need to go back. So
yes.
So this OV and FV, you're saying they are operators acting on C, and this operator.
Yes, OV is this one, and FV is just a function, and just a charge.
Okay.
Yeah, so you are right that if we take this charge and just look at the bracket of this charge with the news, it does not preserve the fall of the Ashtecar-Strobel phase space, and this is something I will come to in some time.
Okay.
Okay, so now but before we do that, before that we will just try to first find the missing vertex, which is classical observable. So we have asymptotic symmetries and quantum soft theorems, but there is another vertex which is the classical low energy observables in the theory. And so let's just to find the vertex, let's just start with the classical conservation law for the super translation charges, which basically tells you that that the total super translation charges chi plus is equal to the charges chi minus, and I have written F for the super translation function on both chi plus chi minus because they are antipodally related. So in that sense, there is only one function. MB is just, I would just like to remind you that MB is just a mass aspect at MB at U. MB of U is mass aspect at U, and similarly MB of B is the mass aspect at B. So the second equality is the analogous to the conservation we get for usual electric charges or total mass, etc. That at U equal to minus infinity, the charge is equal to the charge at V equal to plus infinity. And there is a similar conservation law that we could write down for the super rotation charges. This law has not been understood at the same level. It has not been proved at the same level of generality as the super translation charges, but we just take it as a kind of a proposal that the angular momentum aspect at any angle xa at U equal to minus infinity is equal to the angular momentum aspect at the antipodal angle xa minus xa at V equal to plus infinity. So this is the analogous of this is the conservation law for the super rotation charges. And now we can ask, okay, what does this conservation of super translation charge physically mean? The fact that the mass aspect at u equal to minus infinity at any point of the sphere is equal to the mass aspect at v equal to plus infinity at the antipodal point on the sphere. And it turns out that this statement is really the formula for the memory, in the sense that so the claim is that this conservation law is exactly the formula for the memory. So I'll just try to explain how. So let's consider a generic classical scattering in say 4 or higher dimensions. So we have some n objects, gravitating objects with momentum E1 to Pn, and they could be black holes, neutron stars, whatever. And then there's some strong gravity region. They scatter, and we get the outgoing objects with momentum E1 prime to Pm prime. And then we are interested in looking at the radiation field, which is h mu nu, and we are looking at the radiation data. So in 4 dimensions, we look at the 1 by r component of the field, and I have done a partial Fourier transform from time to omega. So just because we would like to do the soft expansion in the frequency. And so it turns out now that this is just something that one can prove in classical theory for generic scattering, that if you just look at the radiation field in 4 dimensions and you just do this expansion in omega, then the leading term is a pole in omega. This is something actually in electrodynamics Jackson has proved in his book, and where instead of the gravitational field you have just the gauge potential for electrodynamics. And this h mu nu minus 1 has this nice form where you basically sum over all the particles, scattering particles, and in the denominator you have to dot the pi with the vector in which the unit vector at which you are measuring the field, the xi being the point at which you are measuring the classical field. So this is the statement of the classical soft theorem or classical memory. And it turns out that it has been shown that this statement is exactly the rewriting of the conservation of the super translation charge. So this kind of fills the missing vertex, at least for the super translation infrared triangle, that the classical observable is simply the memory effect. So this is just like what I write here, that the super translation conservation law simply computes the classical memory. And so this kind of gives us the explicit characterization of the first infrared triangle, which relates classical memory, Weinberg's soft theorem, and super translation. And now we would like to understand what happens for super rotation. But I can take any question right now for this one. Oh, okay. So then I go on. So let's try to understand what happens in the case of what do the conservation for the super rotation charges, what do they really imply? And I'm going to take a slight detour now. As you will see, it's a little bit as you will see that it will help us understand this conservation a little bit better. So I'm going to look at a case which I call a simpler case, where we look at the classical gravitational radiation in d greater than 4 dimension. And the reason this is a simpler case is because of what Laura mentioned before, that in d greater than 4 dimension we do not have 1 by r effect. So, and that really simplifies the computation for radiation. And this is something that you can actually prove something that we proved with Ashok Sen in 2019, that in a generic classical scattering, gravitational scattering, if you compute the radiation field h mu nu and you do a expansion in omega, then it turns out that not only is the leading term universal, which only depends on the asymptotic momenta, but even the subleading term is universal, and it depends only on the asymptotic momenta and the angular momenta of the scattering particle. And I write down the explicit expression below. So h mu nu 0 is the subleading soft classical radiation in higher than greater than 4 dimension. And as you can see, that it's completely independent of the details of the scattering. It only depends on the asymptotics, and it could be very hard scattering where you could have 2 black holes merging and etc. But this formula would not change. So where these j's are the sum of the orbital angular momentum at infinity, and asymptotic orbital angular momentum, and if your objects at spin, like per black holes, etc., then you have to add that also in the formula. So this is the case of the. So you may wonder, okay, this is a more than 4 dimension, and what has this got to do with the super rotation conservation law? And okay, so the reason this was this a good toy model is that the same result you can show will remain valid if you ignore the Coulombic effects in 4 dimensions. So let's just go with the flow for a moment. Of course, this is something we cannot do physically. We cannot ignore this effect, but just to see what we get, let's just try to ignore this effect. Then then what we see is that modulo this 1 by r effects, we get a universal term even at the subleading order in frequency for the gravitational radiation. And this is what is called the spin memory in the literature now. And it turns out that this statement that H0 mu nu is equal to this term, which is what I call, which is the sum over I, pi, mu, gi, nu, lambda. This statement is equivalent to the conservation of angular momentum aspect at each angle. So the fact that if you ignore the Coulombic effects, then the superrotation charge conservation law gives you precisely the spin memory formula. And so this gives us the missing vertex for the infrared triangle, even for the superrotation. Modulo the caveat that we have dropped the 1/r effects for now. So maybe I stop here and see if there are any questions here. So we have kind of covered all the three vertices a little bit of the infrared triangle for two different asymptotic symmetries, one superrotation and one supertranslation. Okay, then I just go on. Then okay, but this is obviously a huge simplification, because we know that, as Laura mentioned, in 4 dimension, this cannot be quite correct, because this when we start computing radiation, it will get corrected by long range effects, basically 1/r effects. But okay, one interesting thing to notice is that, and we will come to this in more details in a moment, that these effects are higher orders in the Newton's coupling. So if you say that you wanted to somehow compute terms which are 1 pm, 1 post-Minkowski, or linear order in G, then the spin memory is a good classical observable at the leading order in the Newton's constant. And so then these results kind of perturbatively remain valid in the Newton's coupling. I mean, at leading order in the capital G expansion. Okay, so so we kind of now understand how to relate asymptotic symmetries to classical soft theorems. And now, of course, we had the quantum soft theorems, the leading and the subleading quantum soft theorem, and we will try to now see how to relate the the asymptotic symmetries with the quantum soft theorem very fast. So but before doing that, we come to the caveat that Laura mentioned before, that there is an immediate problem before we quantize these charges, is that the action of these charges on the Ashtakashubal phase space is not faithful. And by faithful I mean the following, that on the Ashtakashubal phase space you could compute the Poisson bracket between the super translation charge and the New's tensor, and you get the right answer. But you cannot even compute the action of the super translation charge on the sphere. So it is not defined simply because there is the only elementary bracket which are defined on the phase space are the bracket between the two New's tensors, and there is no bracket. You cannot define the bracket for the shear. Now this is, but in space, from space-time perspective, there is an action of super translation on the shear. So somehow we are missing the action in this Ashtakashubal phase space. So just in more detail, from space-time perspective, we know that the shear changes under super translation by the equation that is written above, and somehow the the Ashtakashubal phase space cannot capture this. Similarly, if we just take the super rotation charge, which was derived by Geoffrey Compere and collaborators and Miguel and others, and if you just compute, let's say, even the bracket between super rotation and the New's, then you immediately see that you get a term which is which is what I have written here, highlighted here, which is constant term in the New's. But this violates the fall off of the New's tensor, which was defined in the Ashtakashubal phase space, because there it is assumed that the New's falls off as some power of u. So so there is a problem with the action. In some sense, there is a problem with both the charges as far as the action on the Ashtakashubal phase space is concerned. Certainly, the supertranslation problem is not that severe, in the sense you may say that I am not interested in the faithful action, but the super rotation issue is more severe because they really just violate the fall off of the speech. So these are the two issues that you would have to tackle before quantizing these charges. And the faithful action would require, so if we even start with super translation, then the faithful action would require extension of this Ashtakashubal phase space, and this was proposed by Hay, Mitra, Strominger, and sorry, I forget another name there. So there were 4 authors who proposed this, and the extension they propose is the following: that you take the Ashtakashubal phase space and you add 2 modes which only depend on the sphere coordinates xa, which are defined as follows. So you take your shear field CAB and look at the the early u limit of the shear field. So what you end up with is the 0 mode of the shear. That's the only thing which will be left, which they call C0. And you take the news tensor and you look at just the zero mode of the news tensor. So you take the news and you integrate it over the entire time. So you get the average, and that is what they call the zero mode of the news. They call it N0. And they showed that you could consistently add C0 and N0 to the asteriskable phase space, and you would get a new Poisson brackets on this extended phase space, which would have the brackets between the shear fields, which were not there in the original phase space, and the bracket between the the constant mode of the shear and the zero mode of the news. And these are the only non-vanishing brackets. I mean, all the other brackets between the other fields vanish. So this was what they this was a proposal they had. There's something that just want to mention, that this is it's not some unique extension or anything. It is just one of the many possible extension, but it is motivated by the requirement that we want the super translation charge to have a faithful action. It should capture the space-time action on the shear. So okay, so and they showed that this extension satisfied this second requirement, and once it did, you could quantize this super translation charge on this extended phase space, and it was shown by these authors that the Ward identity for the super translation charge gives the Weinberg's of Graviton theorem. So I'm just going to sketch the proof very fast, but before that, let me just tell you that this extension does not solve the problem with the super rotation, which really violated the fall off of the, so maybe I should stop here and ask if there are any questions with this extension first.
Just a question, when you say there are many, what do you mean by that? Like
in the sense that these extensions are kind of they have not been somehow like derived from covariant phase space methods, but they have been they have been it is proposed with the requirement that the super translation action should capture the action on the shear. And as you will see now, that there's another extension that that we have, which captures the super rotation, which also captures the super rotation action on the phase space, which is not equivalent to this extension, because we are basically adding boundary terms with the in a way that which satisfies certain requirements we have. So there are many ways perhaps.
Okay. Can you show back the two extensions? One is the
so this one, so far we only discussed one, where you basically add the you add the zero mode of the shear and the constant mode of the shear, and the zero mode of the news.
Yeah. So I had a question about this DADBN. Isn't it the same thing as your TAB?
No. The TAB was DADB of the divergence of the vector field. So it was this n is just the this is just the zero frequency component of the news. NAB, when we integrate NAB over the full scry, we basically just in the Fourier space we get the zero frequency component of the news, and we are just parameterizing them in terms of like one scalar function M0. That's all.
And this C0 and N0, they are going to commute with your TAB, or?
I will come to that. Yeah, they don't quite. That extension is more tricky. Yeah. We will just come to that in a moment. Yeah. Thanks.
And N0 and C are. N0 and
so far,
So
far, maybe I should say that you are right. So far, I have in this page, I have because we started with when we defined gamma 0, we fixed the unit sphere metric, and super translation does not change the sphere metric. So this gamma extension is the extension where the metric is a unit sphere metric. So the TAB tensor is 0. So it don't take into account the TAB yet.
Oh, that's the extension just for BMS. Yes.
Yeah.
One question, Alok, but this is an extension only at the corners. It's not on our full scry, right?
Yeah, it's only exactly. It's the extension which only adds the boundary degrees of freedom at the corners of scry. Exactly.
Okay, so but in general, you would like to have the representation all of scry of the action of translation, super translations, super rotations.
So this one, so the statement is that the once you add these two modes, what you can do is something you could not do in gamma naught, which is that you could define the bracket between shear, like you get these new brackets between the shear n itself, which is the step function basically. And once you have these brackets, you have the action anywhere on u of the super translation on the shear. So the second equation I've written is at any u. So the adding this corner degree of freedom kind of help you in extending even the original brackets in some ways. That you have you have the bracket between not only the news but also between two shear, and it's so. Daniel, was that the question that you were asking? That so
Yeah,
we get the
yeah.
action. Yeah.
Okay.
Yeah,
Thanks.
right. I mean, if you have one corner, you have all corners because you can translate them. So,
Yeah. I mean, the shear mode somehow is, because it's a constant mode. It is all over. It's spread everywhere on Scry. We could think of it like that. Okay. So but now I come to the question. Both Laura and Daniel are kind of hinting at that. Like we for super rotations, we know that we can't first of all ignore T. We have this T tensor. So I just write that the full shear is CAB plus U times TAB. This is how we parameterize the shear. When we don't have a unit sphere metric. And then it turns out that there is an extension that I just schematically write here as gamma tilde, which is the extension which has the zero mode of the shear, the constant, constant mode of the shear, zero mode of the news, and two new modes. One is this T mode, and one is what I just call N1AB, which is just the integral U times NAB. So it's exactly the term that come in the super rotation charge. And then it turns out that adding this mode, we have to do some Dirac bracket analysis, which is a little bit complicated. But once we do that, it turns out that the two modes T and N1 are naturally conjugate to each other. However, there are other non-trivial brackets, which is exactly what Laura was asking. For example, this N1, which is really the subleadings of news, is not quite, it has a non-vanishing bracket, for example, with the C0. So I don't write all the brackets here; they are a bit complicated, but there is a nice extension that we can find, which is self-consistent, which completely closes by itself. And what it achieves for us is the following: that if you consider the super rotation charge, which is where V is a CKV, where V is the the meromorphic vector field, not the smooth vector field, then we can quantize JV. Or in other words, JV has a nice action on this gamma tilde where it preserves the fall off, and and its action captures the action that we expect from space-time of the super rotation. And so once we have that, then we can, once we have that, we can quantize it, and it can be shown that the word identity we get for this super rotation charges, if V is the meromorphic field, can be derived. It is not equivalent, but it can be derived from the subleadings of Graviton theorem, which just for completeness I have written below again. So I just want you to remember that this is really the tree in 4 dimensions. This is the tree level of theorem that was equivalent to the, classically we saw that the conservation law for this mass aspect was equivalent to the the universal spin memory if we ignore the 1/r effect. And so it's really in the quantum side we are really looking at the tree level of theorem. So now okay, so if there is there any question here? Sorry, just because of lack of time, I couldn't go into much detail.
So just a question about N1AB. So that object, in fact, is, I mean, you didn't write it's kind of conjugate to the metric, right?
Yeah. So So N1AB, sorry, I should have mentioned. So N1AB, I just show you again. It is actually, I apologize for that. It is really this term. Just go back a little bit. If you look at this, the second term, which is integral, integral over Scry plus FVAB UNAB, then this FVAB is U independent because it only depends on the sphere metric and the vector field, which are both U independent. So when you integrate over Scry, you have a U integral and you have a sphere integral. So the U integral, this UNAB U integral is what I'm calling N1AB. So it's really the soft mode in the super rotation charge.
Okay, the U integral of that.
U integral. So it is analogous to what
of, in some sense, it's going to be U integral of the double divergence of NAB or something. Is that, or maybe just the U integral?
It's just a U integral of roughly U integral of the shear. Yeah.
Okay.
Okay, sorry, I will go. Mark, you have to tell me when to stop, so I can maybe whenever you want, you let me know.
Yeah, sure. I mean, maybe 5 minutes if you.
Oh, okay. Okay, I'm behind, but okay.
And the convergences of these U integrals are ensured. That's how you restrict your phase space, I guess.
Exactly. Yeah. They're ensured by exactly. Yes. So okay, maybe I skipped this. I wanted to sketch the proof of the Weinberg soft theorem from word identity, but maybe I skipped that. And let me just say one small thing, that one question we did want to ask was that, can all this insight give us a hint into what are all the vacua of quantum gravity? And already we see that once we have the super translation charges and this new extended phase space of Strominger, we can define entire class of vacua, which is basically obtained by, because we have this constant C0 mode, which is a new degree of freedom. We can just translate our vacua using the operator which I've just defined above. FAB is just some smearing function on the sphere. It doesn't depend on U. And if I call that state F, abstractly F, then one can show that these are eigenstates of the super translation charge, and the eigenvalues are given by what I wrote, what is written in the second equation on the right hand side. So there are, this kind of shows that one can immediately check that all the Fs have zero energies, so they are all of course vacuum. So there are infinitely many degenerate vacua which are all parameterized by the eigenvalues of the super translation charge. And one of the questions, of course, that we want to ask, and we still do not understand answer completely, is how do super rotations change the story, and what is the further classification of the vacua once we include super rotation. But now, okay, so I will skip this also, where I wanted to just sketch the proof of the super rotation. The subleading soft theorem from the super rotation charge. But let me say something, because Laura asked that about the Lie algebroid structure. So there was a further subtlety with super rotation which was noticed almost 3 years back by Distler, Flauger, and Hahn, which was the following. They said that okay, let's just work with Astaker-Stubel phase space, and we have all these fall-off issues, but maybe we don't worry about it too much and just quantize the charge on this phase space. That is equivalent to quantizing the charges on just ordinary Fock space. And then let's just compute the commutator of the super rotation and the super translation charges. They did this for really super rotation, where we were just meromorphic vector fields and not smooth vector fields, but the results continue to be valid even when we were just very a smooth vector field. And what they found was that the bracket gives you a super translation charge with a super translation generator, which I call F tilde, which is just given below. It's just some function of V and F. But an extra term which is which they call 2 cocycle, and this k hat is an operator which is linear operator in the soft graviton insertion. So just it's not some C number term, it's not a central extension, it's really an quantum operator, linear operator. And this is of course a problem. So they proved this they proved this result using a very beautiful analysis where they use soft theorems, and they proved this result because because the quantized charge do not preserve the fall off, you may worry how could you derive it, but they use some ingenious identities in soft theorem and prove this. And in the result remain valid whether you whichever extension you use, whether you use the holomorphic vector fields or smooth vector fields. Now, but this poses a serious problem that and this is I think what Laura was referring to before, that since this is an operator and it's not a C number, it doesn't commute with the S matrix. So then we have an issue that we have two symmetries which commute with the S matrix, but their commutators don't commute with the S matrix. But it turns out that there is a nice perhaps way out of this, which was realized by Miguel and Peraza in 2020. That if you work with this extended phase space, that gamma tilde extended, then at least classically the Poisson brackets between the super rotation charge at least for the holomorphic vector fields and the super translation charge actually close, in the sense that the 2 cocycle vanishes. And this is some work in progress where we are trying to show that the quantization also preserves the structure. So the idea was that that because the phase space was wrong, one obtained a wrong quantization of the super rotation charge, which led to this the 2 cocycle. But when we work with the right phase space, which is preserved by the super rotation action, we get a closed algebra and not a Lie algebroid. So let me just summarize at least what I have so far, that we have 2 basic ingredients that we wanted to use to derive these charges and quantize them. One was the fact that we demand that the Hamiltonian action should faithfully capture the space-time action on the shear field, and that word identities should be equivalent to, or capture, at least give us consistent with soft theorem. and they lead to this phase space, which we are calling gamma tilde extended, which has the shear field, which has this, the C0, which is the constant shear mode, N0, which is the soft news, N1, which is the integral U times N, and TAB, which is the T tensor. And so far we have got a class of soft vacua which are parameterized by super translation charges, eigenvalue of super translation charges. And now we can ask, okay, can this vacua be classified even further because we have if we have super rotations in the game? Now it turns out that at least on this extended phase space, that T tensor commutes with C0, which is the constant shear. And in fact, it turns out that if you take V to be holomorphic vector field, then this T tensor has a nice form, which is a Schwarzian, which is discovered by Nguyen and Salzar in this paper in 2019. So it gives us a hope that maybe the vacua are parameterized not only by by C0 modes, but also by the tensor T, and so that could be a further classification of the vacua. And but this is open. The analysis has not completely been done. I should mention that at least in non-abelian gauge theory, there is a rigorous construction of this gamma tilde extended, which was done by Prahar and Temple in very recently. Okay, and maybe I just end with this one, that so we have some handle on this second infrared triangle, which relates the super rotation charges, the spin memory effect, which is valid really only to first post-Minkowskian expansion, or if we ignore the 1/r effects, and the Kajazo-Strominger quantum soft theorem, which is a tree-level soft theorem for scattering amplitude. And something that Ashok and I showed in 2018 is that there is a nice way that we could take a classical limit of this quantum soft theorem and really derive this universal spin memory effect. Okay, maybe I just end here. I wanted to say something about the log stuff, but I ran out of time. So maybe I'll stop here, Mark.
Yes, thanks. Look. So we have time for questions now.
Hi, Alok.
Hi.
One question is, what's the state with superboost? You only mentioned super rotations, but
sorry, for me super rotation include superboost.
Okay.
I just they include all vector fields on the sphere, not just the rotation ones. Yeah, I mean okay. I just call super rotation. Right?
Okay.
So yeah, did you end up mentioning the physics of the log term?
Yeah, I ran out of time. I'm sorry about that. So I think I prepared like 2 hours talk for a 1 hour talk. Maybe I just say, since you asked, maybe I say something about the physics of the log, where it comes from. Just say it here. I mean, the basic idea is very, very simple, at least for the classical theory, that when we look at classical scattering of say n objects, and they scatter into m momenta, then there are 2 Coulombic effects which are in play. One is the Coulombic 1/r effect between the scattering particles themselves. So no matter how far apart they are in asymptotic past or future, they are never free. And this is explicitly seen if we study trajectory of these particles, which I have written here. So if you just look at asymptotic trajectory of a particle, then you explicitly see that there is an acceleration term which goes as log of t, which is not present in higher dimension, because this term precisely comes from the 1/r potential, gravitational potential. And there is another effect which is usually called the phase term in the post-Newtonian literature, which is the Coulombic effect of the particles on the gravitational radiation itself, which I denote here with the green dot. So red lines are the gravitational radiation, and the green dot is the Coulombic drag, and that manifests itself as a phase in the gravitational radiation, which goes as log omega r, capital R just being the distance of where we are sitting, detector is sitting from the scattering center. So these 2 are the effects which both of these effects. So intuitively you see where log omega could come from. So the phase itself explicitly has a log omega, and the trajectory has a log t, but it's a log t at late times. So if you go to Fourier transform, then large t becomes small omega inverse, So wherever you have a log t, it becomes log omega inverse, which is minus log omega. So both of them contribute to log omega. I mean, this is one intuitive way to understand where the log come from. I don't know, Mark, if that answer your question.
Yes, a bit. Thanks.
A question about that. If you have log terms, then you have necessarily conformal anomalies, right?
In the sense that you're saying that the charges will not be conserved, or
well, first it means that all the other, if you have only algebraic term, then it's under rescaling of omega.
Yes.
All these
Yes.
transform tensors. But now there's like you have a term c here. So then if you change the scale, then you're going to have constant term floating around.
yes,
constant
yes.
space term, which are exactly what anomalies are like. So
okay, but
anomalies in the transformations, and then presumably, yeah, the question is how much of this C is really an anomaly in the algebra.
Okay. I think this is completely open. I don't think there is any answer to this, but maybe since you asked, I can say something that there was one thing that Miguel and I investigated a couple of years back, is that do these logs of theorem come from what identities of some charges? So although we do not know what the underlying symmetries are, we wanted to know if there are some conservation laws which are equivalent to the soft theorems. And we did not do this in gravity, because just in gravity there are two logarithmic effects. One is the Coulombic drag between scattering particles, and one is the Coulombic effect of the particle on the radiation. If you instead of working QED, then you have only one Coulombic effect, which is the C effect. This phasing effect is absent. And there we could show that, so maybe I just show you the expression that we could show that there the soft effects could be captured by a Ward identity, where the conservation law, I just show it here. So I'm just showing the conservation law. So the point is that if you are in QED and if you look at the asymptotic fields, then you can show that there is a conservation law which is such that if you look at this FRA term of the electromagnetic field, then because of the Coulombic effect, this field diverges as log u h chi plus, and diverges as there's a log r dependent as chi minus. But you can show by equations of motion that these two modes are equal at each xa. So you have an infinity of conservation laws in QED, at least once you take this Coulombic drag into account. Now you can ask whether you can quantize this charge. This is something that Miguel and I tried to do in our paper, and we showed that indeed the corresponding Ward identity actually gives us the logs of theorems, at least for the photon case, which is much simpler. So, but what we do not understand is what is the algebra or the symmetry, which is related to the question you are asking. So, these logarithmic charges seem to have no good action on the Astaker-Struble type phase space, or even in the new extensions we have. So it is possible that these symmetries are anomalous or something, but at least we could find some conservation laws. So the status is that we have some conservation laws, but we do not know if they represent any asymptotic symmetry for this block from here. Yeah. So that's open. So that's maybe I just show it here. So here is the kind of the status of the what I would call infrared triangle 3, which is the which is the infrared triangle for the loop corrected soft theorems, both in QED and gravity, where we have the logs of theorems in the quantum theory, and there have been the classical log radiation, which has been derived completely rigorously by Ashok Sen and his collaborators, both in gravity and electrodynamics. So but this triangle doesn't close in the sense that we don't know what the symmetry is, and we also don't know how the classical limit of the quantum logs of theorem gives us the classical radiation. Even that is not completely understood. So this triangle is kind of almost everything remains to be understood in this triangle. I mean, the vertices are understood thanks to work of Ashok and his collaborators, we know the charges, and most of the charges have been derived by actually a graduate student in India, Sayali, and but we don't understand the symmetries, and we don't know how these different vertices are connected to each other. So yeah.
Thank you. Yeah, that's very nice. Well, one thing it suggests, the physical argument you presented, that
Yes.
somehow the scattering of the Coulombic field of the radiation.
Yes.
It seems that it's important in the sense that it violates the usual notion of asymptotic flatness.
Yes.
Exactly. Assumes. So does that mean that this mathematical assumption, in fact, is wrong? like it's very nice mathematically, but it doesn't account for the physics of gravitational radiation.
Yeah, I mean, I think that this is, I'm a bit hesitant to, I mean, I think, yeah, I'm a bit hesitant to say
yeah,
that.
that's why I'm pushing you. I know, if you're saying there's log terms there, you're saying Penrose was the definition we use for something.
So I would not want to be killed by relativists. So I would let me answer the question in a different way. That we know that if we compute the amplitude, we know that these amplitudes are infrared divergent, like perturbative gravity or QED amplitudes, and we know that the source of that is that we assume that the scattering states are free. And of course, as you know that the scattering states are not free because they are dressed by cloud of soft particles. And so if you use these covariant states, which is what Coolidge and Faddeev showed, then we do get the infrared finite S matrix. So from that perspective, we know that it is a wrong assumption to assume that the fields are free at late times. So I do think that those follow-ups has to be modified, but I don't know if anyone has actually studied what the modified follow-up at Scry should be. Yeah.
Can I think of it as reconciling, saying that Penrose boundary condition, like with no log, is a classical statement, and then
no, but this is also classical, because the fact is that this is it is both classical and quantum. So it is certainly the effect which manifests itself as the classical effect in the C term in the trajectory and the phase term in the radiation in this and in the quantum theory manifests itself in the fact that the asymptotic Hamiltonian is not free, and it has a interaction.
If it's classical, then it's problematic, because it really means that the thing we are using is completely wrong.
I mean, if you take this effect into account,
When I look at your diagram, like the red, white, and green line from a loop, so maybe I can think of that as quantum. Is that the way?
No. I would say still it is true in quantum, but it is also so there. Of course, as you know, there are many quantum infrared effects which survive in the h bar going to 0 limit, and these are precisely those effects. So they are effects which come from loops, but because these are IR effects, they don't go away in the classical limit, and they really survive. So if you do explicit classical computation, so there was there is, I mean, these tales of course have been noticed before in the classical GR literature, and this paper of P.C. Peters, where he look at gravitational Bremsstrahlung of a point particle in Schwarzschild space-time. He gives integral formula for H mu radiation in 4 dimensions. And you can just, if you take the low frequency expansion, you can explicitly see that you get a log omega term in his radiation. This is I think that
So you're saying there's a classical configuration which already violates, like
yes, certainly. So
violates asymptotically flat boundary conditions.
So asymptotically flat, it doesn't violate, but I think these fall-offs that we assume in the no, I don't mean asymptotically flat, but the fall-off on the shear that we assume at large U, I think that it probably violates. Yeah.
Okay. I have another question, but I asked many questions, so maybe. Okay, I have a question about the Distler calculation.
Yes.
So you say you can, when you extend, you don't have the symmetry. I mean, you find no, you don't find this anomaly.
Classically, certainly it was shown by,
So, but the Distler calculation seems surprising, because a priori they're working with the S matrix. So a priori the S matrix should have everybody there. So how do you understand the result? Is it because their definition of the S matrix is wrong, or because if you have the right definition of the S matrix, then you're fully extended, right? The S matrix by definition is the guy which is fully extended. So
the S matrix is fully extended. That's true, but the charge is the question is that the definition of the charge that you have used is perhaps maybe that's one way to say it. The charge definition that you use is not correct. So what Miguel and Javier showed is that actually the JV that you find which satisfies equation 1 here, that JV has a corner term, extra corner term, which was not there in the old JV that people were using, including Distler and Horn, and that is what will will change the result. So we are not completely sure with our proof, but we also seem to get after quantization the fact that this classical structure is observed is valid. but it's much more subtle than the classical analysis. So yeah, so it's not completely clear yet. So,
thank you. That's very nice. Thanks, Alok.
thanks. Yeah.
So if there are no more questions, I can thank Alok again.